Welcome to SDN Tech Networking Podcast, world's first human-curated AI podcast.
Hey everyone, welcome to another deep dive with us. Today we're tackling something that's both familiar and kind of mysterious: computer networks.
Yeah, like we all use them every day, but how many of us actually know how they work?
Exactly. So ready to get our hands dirty and uncover the secrets of the internet.
Absolutely, let's dive in.
All right, so one of the first things that popped up in the material was this idea of layering and abstraction.
Oh yeah, that's a fundamental concept in networking.
But it sounds kind of intimidating, honestly. I'm not sure I even remember what abstraction means.
It's actually pretty simple. Think of it like this: when you send a letter, you don't need to worry about how the postal service gets it to the destination.
Right, I just write the address and stick it in the mailbox.
Exactly, you're abstracting away all those complex details of sorting, routing, delivery trucks, and so on.
So it's about simplifying things by hiding the unnecessary details.
Precisely. And in computer networks, this layering concept is what allows different systems to communicate with each other without needing to know everything about how the other system works.
Okay, that makes sense. So in the letter analogy, what would the different layers be?
Well, writing the letter, that's the application layer.
Got it. That's the actual content I want to send.
Then you put it in an envelope and write the address. That's like the transport layer.
So the address tells the postal service where to send it, right?
Yep, that would be the network layer, handling the actual routing and delivery across the postal network.
And then finally, you've got the mail carrier physically bringing the letter to the recipient's doorstep. That's got to be the link layer.
Exactly. Each layer has its own specific job, and they all work together to deliver that letter.
So it's like a well-coordinated team, each layer focusing on its own task.
Precisely. And this same principle applies to the internet, just on a much larger and more complex scale.
Okay, that's a pretty cool way to think about it. But how does this actually play out when I'm, say, browsing the web? It's not like there are tiny mail carriers running around inside my computer, right?
Haha, no, not quite. But the principle is the same. When you access a website, your request travels through these different layers. Each layer handles a specific aspect of the communication.
For instance, I've heard of DNS. Where does that fit into all this?
Ah, DNS. That's a crucial part. It's like a giant phone book for the internet. It translates those human-readable website names like google.com into numerical IP addresses that computers use.
Oh yeah, those IP addresses. They look something like 192.168. Something. Not exactly easy to remember.
Definitely not. But computers need those numerical addresses to communicate. So DNS is like the postal service looking up the recipient's address based on their name.
So what happens after my computer gets the IP address from DNS?
Well, it needs to establish a connection with the server hosting the website. That's where TCP comes in.
TCP. The Transmission Control Protocol vaguely rings a bell. Isn't that all about reliable data transfer?
You got it. TCP ensures that all the data packets arrive at the destination in the correct order and without any errors.
Oh, so it's like a guarantee that my cat video won't turn into a jumbled mess.
Pretty much. It's crucial for things like web browsing, file transfers, anything where you need data to be transmitted reliably.
Okay, I'm starting to see how this all fits together. But how does TCP actually ensure that reliability? Does it, like, send a scout ahead to check the route?
Haha, not exactly. It uses a system of acknowledgments and retransmissions. When your computer sends a packet of data, the server sends back an acknowledgment confirming that it was received.
So it's like a, hey, got it message.
Yep. And if an acknowledgment isn't received within a certain time, TCP automatically resends the data.
Smart. So it's constantly checking to make sure everything arrives safely. But what about this sliding window protocol thing I saw mentioned in the notes? Sounds kind of mysterious.
Ah, the sliding window. It's actually a clever way to improve efficiency. Imagine you're sending a bunch of data packets. Instead of waiting for an acknowledgement for each individual packet, the sender can send multiple packets within this window.
So it's like sending a batch of letters at once instead of one by one.
Exactly. This significantly speeds up the data transfer process because you're not constantly waiting for those acknowledgments.
I see. But doesn't that increase the risk of data getting lost or corrupted?
It could, but TCP's got that covered too with its congestion control mechanism.
Okay, so TCP is like a super cautious delivery service and make sure the package arrives intact, and it also avoids clogging up the roads.
A perfect analogy. TCP is constantly monitoring the network for signs of congestion and adjusts its data flow accordingly.
So it's like those smart traffic lights that adjust their timing based on traffic volume. Pretty neat.
Yeah.
But what if there are other applications using the network that aren't as well behaved? Does TCP just have to suffer the consequences?
That's a great question. And it brings up the issue of fairness in network resource allocation.
Fairness. like making sure everyone gets a fair share of the bandwidth.
Precisely. TCP's congestion control mechanism aims to be fair by having everyone back off equally when congestion occurs.
So everyone has to slow down a bit when things get crowded. Makes sense. But are there any other ways to manage network traffic? Like, what about protocols that aren't as focused on reliability?
You're thinking of UDP user datagram protocol. It's like sending a postcard. You hope it arrives, but there's no guarantee.
Ah, I see. So it's faster and more lightweight, but it doesn't have the same level of reliability as TCP.
Right, UDP is often used for things like video streaming or online gaming, where speed is more important than guaranteed delivery.
So it's a trade-off, speed versus reliability.
Exactly. And that's one of the ongoing challenges in internet engineering, finding the right balance between the different types of traffic and ensuring that everyone gets a fair share of the bandwidth.
Okay, we've covered layering DNS TCP. This is already way more than I ever knew about how the internet works. But there's got to be more, right? Like, how does my data actually find its way through this vast network of interconnected computers?
Well, that's where routers come in. They're the traffic directors of the internet.
Routers.
Yes.
Those little boxes we have in our homes.
Yep, those are a type of router. They determine the most efficient path for your data packets to travel, forwarding them from one network to another until they reach their destination.
So it's not just a direct connection from my computer to the website server. My data is actually taking a scenic route.
More like hopping on a series of connecting flights. Each router along the way makes decisions about the best path based on network conditions, available bandwidth, and other factors.
Wow, it's amazing how it all happens so seamlessly in milliseconds. I click a link, and boom, there's the website. I never realized how much work was going on behind the scenes.
It's pretty incredible, and there are tools you can use to actually see this routing process in action.
Oh yeah, like what?
Well, you mentioned ping and traceroute earlier.
Right, I've definitely heard of those.
Yeah.
But honestly, I'm not entirely sure what they do.
Ping is like sending out a sonar pulse. It sends a tiny packet of data to a server and measures how long it takes to get a response.
So it tells you if the server is reachable and how long it takes to get there.
Exactly. It's a quick and easy way to check network connectivity.
Okay, and what about traceroute? What's that all about?
Traceroute is like dropping breadcrumbs along a path. It maps out the entire route that your data takes from your computer to the destination server.
Whoa, how does it do that?
It uses a clever trick with something called time to live, or TTL. Each packet has a TTL value, and each router it passes through decreases that value by 1.
Okay, and then what?
When the TTL reaches 0, the router sends back an error message. By sending out packets with progressively increasing TTL values, traceroute can figure out the path.
Ah, I see. It's like sending out scouts, each one going a little further until one of them reaches the target and reports back.
Precisely. It gives you a fascinating glimpse into the hidden infrastructure of the internet.
This is so cool. I'm going to have to try out these tools and see what routes my own data takes.
Yeah.
But what about if you want to test and experiment with networks in more depth? Do you have to build a whole physical network with cables and routers for that?
Not necessarily. We've also got some material here on Mininet.
Mininet, what's that?
It's a software tool that lets you create virtual networks. You can build and test complex network topologies without needing any physical hardware.
Wow, so it's like a simulator for networks.
Exactly. Researchers and engineers use Mininet to experiment with new protocols, analyze performance, and troubleshoot problems, all within a safe, virtual environment.
That makes a lot of sense. It's much easier and cheaper than building a whole physical network every time you want to try something new.
Absolutely. And speaking of trying new things, what about routing algorithms? They seem pretty crucial for managing all this data traffic.
Routing algorithms, are those like the GPS for data packets?
That's a good way to think about it. In a network with multiple possible routes, you need a way to find the best path. That's where routing algorithms come in.
So it's about finding the shortest route, just like on a map.
Yes, but it's not just about distance. Routing algorithms consider factors like network congestion, link bandwidth, and even the cost of using a particular link.
I see. So it's like finding the fastest route, but also taking into account tolls and traffic jams.
Exactly. And there are different algorithms for different situations. Two common ones are Dijkstra's algorithm and the Bellman-Ford algorithm.
Okay, those names ring a bell from my computer science class,
Mm-hmm.
but I could definitely use a refresher on how they actually work.
Dijkstra's algorithm is great for finding the shortest path in a network with non-negative link weights. Imagine a network like a map where roads have different lengths. Dijkstra's algorithm helps you find the shortest path from one point to another.
Okay, that makes sense. But what about Bellman-Ford? What's its specialty?
Bellman-Ford can handle negative weights as well. Imagine there are toll roads on your map. Sometimes taking a slightly longer route to avoid a toll road might be cheaper overall.
Ah, I get it. So negative weights represent things like congestion or high costs that you might want to avoid, even if it means taking a slightly longer path. Pretty clever. But are these algorithms actually used in the real world?
Absolutely. They're implemented in real-world routing protocols like RIP and OSPF, which are used to manage internet traffic on a massive scale.
That's incredible. It's amazing to think that these algorithms are the brains behind how data gets routed across vast networks, ensuring it reaches its destination efficiently and reliably.
Okay, we've covered layering DNS TCP routing algorithms. What else should we explore before moving on to the next level of this deep dive?
One more crucial concept, TCP and reliability. We talked about TCP ensuring data delivery, but there's more to it than just acknowledgments and
Well,
retransmissions.
there's always more to learn. I'm ready to dive deeper into the world of TCP.
So ready to unravel more of those TCP mysteries? Definitely. You mentioned there's more to TCP's reliability than just those acknowledgments and retransmissions, right?
Absolutely. Let's imagine you're sending a huge file over the internet.
Like a massive cat video compilation.
Sure. Now, it wouldn't be very efficient to send one tiny packet and then just sit there twiddling our thumbs waiting for the acknowledgement before sending the next one.
Right. Talk about a snail's pace internet.
Exactly. So TCP uses this cool thing called flow control to manage how fast the data is sent.
Flow control, is that like a speed limit for data?
It's more like a polite conversation where both sides agree on a comfortable speaking pace.
I like that analogy.
The receiver basically says, hey, hold up a sec. I need a moment to process all this before you keep going, so the sender knows not to overwhelm the receiver.
So it's about making sure the receiver doesn't get flooded with more data than it can handle. Makes sense. But what happens if the network itself starts getting clogged, like a digital traffic jam? Does TCP just keep blindly sending data?
That's where TCP's congestion control mechanism steps in. It's constantly monitoring the network for any signs of trouble.
Like a digital traffic cop?
Precisely. It can detect things like increased delays or packet loss, which are signs of congestion.
And then what? Does it start handing out digital speeding tickets?
Not quite, but it does tell everyone to slow down a bit. It reduces its sending rate to help ease the congestion and keep things flowing smoothly.
So TCP is not only about reliable delivery, but also about being a responsible member of the internet community. No road rage here.
Exactly. It's all about sharing the road and making sure everyone gets where they need to go. But this makes me wonder, doesn't this mean TCP traffic can be slowed down by those who aren't playing by the rules? We were talking about UDP earlier.
Right, UDP is like sending a postcard. You just fling it out there and hope for the best.
Exactly. It's faster and more efficient for some things, but it doesn't have those same reliability and congestion control features as TCP.
So it's like some cars weaving in and out of traffic, causing everyone else to slam on the brakes. A bit chaotic.
A good analogy. It's an ongoing challenge to find the right balance between these different types of traffic. It's like a never-ending game of traffic management on a global scale.
Makes you appreciate all the effort that goes into keeping the internet running smoothly.
Yeah.
Okay, shifting gears a bit. What about this stuff on overlays and virtualization? Those sound pretty high-tech.
They might sound complex, but the idea is actually pretty simple. Think of your home or office network. An overlay network is built on top of that existing network to add extra features and functionality.
So it's like building a secret network on top of the regular one.
That's a good way to put it. One common example is a VPN, or virtual private network.
VPNs. I use one all the time, especially on public Wi-Fi. Keeps things nice and secure.
Exactly. A VPN creates a secure, encrypted connection over the public internet, like building a private tunnel through a busy city.
Love that visual. So only authorized traffic can pass through this tunnel.
Exactly, making it much harder for snoopers to peek at your data.
Okay, VPNs, I get it. Any other examples of these overlay networks?
Another one is VLANs, or virtual LANs. Think of it like dividing a big office building into separate departments, each with their own network.
So instead of everyone being on the same network, you can create smaller, isolated groups.
Precisely. It can improve security because a problem in one VLAN won't affect the others. And it can boost performance, too, by reducing congestion.
Right, like preventing one department's massive file transfers from bogging down everyone else.
Exactly. Now, these VLANs are often implemented using switches.
Switches, aren't those just like those little boxes that connect multiple devices together?
They are, but they can do more than just connect. They can tag traffic with a special VLAN ID.
So it's like giving each VLAN its own color code, and the switch makes sure only packets with matching colors can talk to each other.
You got it. Now, there might be times when devices on different VLANs need to communicate, right?
Yeah, like if two departments need to collaborate on a project, how would they connect if they're on separate networks?
You'd use a layer 3 switch, which is basically a router. It acts like a translator between departments, ensuring that communication flows smoothly.
So you can keep the benefits of separation while still allowing communication when needed. That's pretty neat. Anything else with these overlays?
There are plenty, but let's move on to something related. Network Address Translation, or NAT.
Ooh, NAT. Heard of it, but not exactly sure what it does. Something to do with IP addresses, right?
You got it. NAT lets multiple devices on a private network share a single public IP address.
Wait, share an IP address? I thought every device on the internet needed its own unique one.
You're right, they do.
Good.
But NAT allows those devices to share when communicating with the outside world. Think of it like an office mailroom.
Okay, I'm intrigued. Go on.
NAT is like the receptionist handling mail for everyone in the office using a single external address.
So it's like a single phone number for the entire office, but each person has their own extension.
Perfect analogy. When a device inside the private network wants to send data out, the NAT device swaps its private IP address with the public one and adds a unique port number.
So it's like a super organized receptionist who always knows exactly who to forward each message to.
Precisely. It keeps a careful record of which device is sending what, making sure the responses get back to the right place.
That's pretty clever. Why is this whole NAT thing so important, though?
Well, remember how we're running out of those IPv4 addresses?
Right, because every device needs an address, and we're kind of running out of numbers. But what about IPv6? Isn't that supposed to solve all our IP address woes?
It is. IPv6 has way more addresses, but the transition is taking a while. So for now, NAT is crucial for making the most of those precious IPv4 addresses.
So NAT is like squeezing a whole bunch of people into a tiny car just until we can get a bigger one.
A very creative way to put it. But I'm sure you're thinking, there's got to be a downside to all this, right?
Yeah, it can't all be sunshine and rainbows.
Yeah.
What are the drawbacks of NAT?
Well, one issue is that it can add a tiny bit of delay, as each packet needs to be checked and translated by the NAT device.
I guess a few extra milliseconds is a small price to pay for the benefits. Anything else?
Another thing is that NAT can sometimes mess with applications that need a direct connection, like peer-to-peer file sharing or online gaming.
Because the NAT device is acting like a gatekeeper, right? It can make it difficult for devices outside the network to directly reach those inside.
Exactly. So NAT, while super useful, isn't a perfect solution.
Makes sense. It's all about trade-offs, isn't it? Wow, this is really making me appreciate the complexity of networking. So what's next on our deep dive agenda?
Let's jump into the future of networking software-defined networks and network function virtualization.
Ooh, those sound super high-tech. I'm ready for a brain upgrade.
Yeah.
Okay, so SDN and NFV software-defined networks and network function virtualization. Those sound like something out of a futuristic tech thriller.
Yeah, they have a kind of sci-fi vibe, but the ideas are actually pretty easy to grasp.
So break it down for me. What are they all about?
Okay, so traditionally, network devices like routers and switches, they've had their smarts, their control logic, baked right into the hardware itself.
So it's like trying to upgrade your computer by literally rewiring the circuits.
Exactly. Not exactly flexible or user-friendly, right?
No, definitely not. So how do SDN and NFV change that?
Well, SDN, software-defined networking, it basically says, hey, let's separate the brains from the brawn.
Intriguing. By brains, you mean the control of the network.
Exactly. It separates the control plane from the data plane.
Okay, hold up. Control plane, data plane. Those sound like something out of Star Trek. What are they exactly?
All right, imagine a highway system. The data plane, that's like the actual roads and highways where the data flows. The control plane, think of it as the traffic management system, the one that monitors conditions and sets speed limits.
Ah, okay. So SDN is like having a central control tower overseeing the entire network instead of each intersection having its own independent traffic light.
Exactly. SDN centralizes the control logic in a software controller, basically a program running on a server somewhere.
So instead of manually configuring each individual router and switch, you can control everything from this central software controller.
Exactly. Way more efficient and flexible.
And what's the benefit of that?
Well, for one, you can automate a lot of network management tasks. It also makes it easier to do things like traffic engineering, optimizing the flow of data across the network, and you can even create custom network services tailored for specific applications.
Wow, so it's like having a super smart traffic management system that can adapt to changing conditions in real time. Sounds pretty amazing. But I got to ask, is this really the future of networking? Are we really on the verge of a lag-free, always connected utopia.
Well, maybe not a complete utopia, but SDN definitely has the potential to revolutionize how we build and manage networks. And it works hand in hand with NFV network function virtualization.
Right, NFV, what's that all about? Is it about virtual reality networking?
Haha, not quite. But it does involve virtualization. Think about the way we use virtual machines for servers and operating systems.
Right, you can run multiple virtual servers on a single physical machine.
Exactly. NFV takes that same idea and applies it to network functions. Traditionally, you needed dedicated hardware for things like firewalls, load balancers, intrusion detection systems.
Yeah, all those boxes with blinking lights taking up space in the server room.
Exactly. But with NFV, you can run these network functions as software on virtual machines.
So instead of a bunch of separate hardware appliances, it's all just software running on a few servers.
Precisely. This makes everything way more flexible and cost-effective.
I see. You can easily spin up new network functions as needed without having to buy and install a bunch of new hardware.
Exactly. And you can scale those functions up or down as demand changes.
It's like having a virtual toolbox of networking gadgets that you can just plug and play as needed.
Great analogy. And by combining SDN and NFV, you can create a network that's truly dynamic and adaptable. It can respond to changes in real time and optimize itself for different applications and workloads.
This is mind-blowing. It's like the network becomes a self-driving car, constantly adjusting and optimizing itself for the best possible performance.
You're getting it. SDN and NFV are still relatively new technologies, but they're quickly gaining traction as businesses and organizations start to see the benefits.
I can see why this is like taking the internet to the next level. Smarter, more efficient, more powerful. It's really exciting to think about the possibilities. But what does all this mean for everyday internet users like me? Will we actually see the impact of SDN and NFV?
You probably won't notice a sudden, dramatic change. But behind the scenes, SDN and NFV are working hard to make your internet experience faster, smoother, and more secure.
Well, in that case, I'm happy to let the experts handle the technical details while I just enjoy a seamless online experience. This deep dive has been incredible. We've gone from the basic building blocks of computer networks all the way to the cutting edge of SDN and NFV. I feel like I've leveled up my understanding of the internet.
We've covered a lot of ground, but there's always more to learn. The world of computer networks is constantly evolving.
Well, I guess that's the beauty of it, right? There's always something new and exciting to discover. And that's it for our deep dive into computer networks. Until next time, stay curious and keep exploring.